Okay, so today we are naming and writing reactions for carboxylic acids and esters. And this is our last lecture of the elementary organic part. After this, we begin the biochem half of the semester. So we're going to do this week focusing on carboxylic acids and esters. And again, we're focusing on this from an elementary organic standpoint. So if you're watching this video as a organic student, the way you talk about carboxylic acids and esters in organic chem is going to be at a deeper level than the way we would look at them at the elementary organic level. So just a word to the wise there. So when we talk about carboxylic acids and esters, they're analogous to aldehydes and ketones in the sense of, remember aldehydes were at the end of the chain, right? Well, a carboxylic acid is also at the end. And a ketone is in the middle, right? Well, an ester is in the middle. Right? So aldehydes are carboxylic acid analogs, and ketones are esters analogs, right, in terms of where they're located. So when we're looking at molecules containing carboxylic acids versus molecules containing esters, right, a carboxylic acids are going to be on the end, just like an aldehyde is going to be on the end, and an ester is going to be on the interior, just like a ketone is going to be on the interior. Right? So they are analogous to each other in that regard. And so let's look at just carboxylic acids first. We write out the carboxyl group as C double bond O OH. So you might see it written out as COOH, or some books even write it as CO2H, right? A lot of students misidentify this. If I say, what functional group is this? They'll say, oh, it's I don't know, a ketone and an alcohol. But that's not correct, right? When these two are together, that is one functional group called the carboxyl group or the carboxylic acid group. Okay, that's why it's COOH or CO2H. They're very, very, very polar. Right? If we think back to our intermolecular forces, you've got dipole-dipole coming from this piece right here, and you've got hydrogen bonding coming from this piece right here. So in terms of their boiling points, would you expect them to be high or low? Very high, right? They're going to be even higher than alcohols and amines. So far, those are the highest boiling points we've seen this semester, right? Alcohols and amines have hydrogen bonding. Well, a carboxylic acid has hydrogen bonding as well, but it also has dipole-dipole. So it's like the king in terms of who's going to have the highest boiling point. If we have 3 or 4 molecules of all similar sizes, of course, right? One of them can't be part of a 20-carbon chain and the other part of a 3-carbon chain. That wouldn't be fair. But if they're all similar sizes, one's an alcohol, one's an amine, one's a carboxylic acid, and I said, who's the highest? The carboxylic acid's going to boil higher than both the alcohol and the amine. And so here are some data. Right, so here's butane, wimpy little butane, boiling point of -0.5 gas at room temperature. There's an ether, right? We said ethers have a very weak dipole-dipole, very weak. Notice it only brought you up 7 degrees, or 6.5. 7.5, I mean. Then we jump up a good bit when we get to the aldehydes and the ketones, right? There's an aldehyde at 49. There's a ketone at 56. It's a significant jump from here. And there's a significant difference between these two, right? And then you jump again when you get the alcohol involved, 1 propanol. And then when you get the carboxylic acid involved, you get a big jump too, right? So all 3, hydrogen bonding, dipole-dipole, weak dipole-dipole, and then London only. And again, just like solubility of all the other ones we've seen, that chain length needs to be 6 or less. Why is 6 the magic number? Because after 6, when this chain gets to be too long, what happens? It becomes too nonpolar, right? The nonpolar component can't be outweighed by the polar component. Right? Because this is the polar component here. This is where all the hydrogen bonding is taking place. If this chain gets to be too long, well, now this chain is not capable of hydrogen bonding. So now it becomes a barrier to solubility, right? Because this piece down here is too nonpolar to offset the polar part. And this figure's in your book, right? So methanoic, ethanoic, propanoic, butanoic, pentanoic, where yes. At butanoic, we start getting slightly, and then after that, it would be insoluble.
So is the OIC the suffix?
Yep, we're going to talk about that in just a second. Just want to throw this out here now because we'll see this in the biochem section when we start next week. When we have a carboxylic acid with a big long chain, right, so greater than 10 usually is where we start calling it a long chain, we call those fatty acids. And that's going to be a big part of what we're talking about next week in biochem. That's the first biomolecule we'll look at, are fatty acids. So just throwing that out here, right? This is what we're talking about. Carboxyl group with a big long chain, we call those fatty acids. And that's where we're going to start the biochem section, is with this, since we're leading off with it, I mean, since we're finishing this week. So how do we name a carboxylic acid? It's pretty easy. By definition, the carboxyl carbon is number 1. Just like when we named aldehydes, right? The aldehyde carbon was number 1 by default. Why? Because the aldehyde's on the end. We're only naming molecules with one functional group, so we don't need to worry about, multiple functional groups going on. So by default, the carboxyl carbon's number 1. Then if we have any substituents, we would locate them, put them with numbers, so 2-chloro or 4-methyl or whatever, right? And then your suffix is oic acid. So if you had this molecule, right, here's carbon number 1. A lot of students misidentify the length of the chain. For some reason, they want to call this carbon 1, but that's not a carbon, right? That's an oxygen atom. So the carboxyl carbon, the carbon that has the COOH, excuse me, that's carbon number 1. So 1, 2, 3, 4. So 3 bromo, and then this is a 4-carbon chain, butanoic acid. Easy enough? It's basically the same as naming aldehydes, right? It's just a different suffix. So I'll pause the video and give you a chance to try naming these two. All right, let's name these two molecules. So when we're naming these two, picking carbon number 1 doesn't take a whole lot of effort, right? Because all we need to do is find the carboxyl group. So we're going to name from the left or from the right? From the right. So 1, 2, 3, 4, 5, 6, 7, 8. All right? And so what are our substituents? So it would be what numbers?
4, 7.
Right, 4, 7, dibromo, right? Then what? 5 ethyl. And then what?
Is it octanoic?
Octanoic acid. And then here, again, carbon number 1's easy. 1, 2, 3, 4, 5, 6, or 5, 6, 7. We have 7 carbons, right? 5, 6, 7. So what's the name of this?
4,
5 dimethyl, right? And this is a 7-carbon chain. Hexanoic acid, right? Good. Do we feel good about naming these? So no worse than naming aldehydes, right? In terms of locating carbon number 1, it's going to be the one with the functional group. And then all you need to do is worry about any substituents you might have. And obviously your parent chain, just pick the longest one, right? Okay, I'm going to let you try these. Go. I'll pause the video and let you try these. All right, let's look at what we've got here. Hexanoic acid would be how many carbons? 6. That's a 6-carbon chain. So 1, 2, 3, 4, 5, 6. And now you can choose carbon number 1, whichever end you prefer, right? So let's just make number 1 over here. Okay, so 3, 3, 5 trimethyl. So 1, 2, 3, 3, 3, 4, 5, 5 trimethyl, and then 2-chloro. So there's that one. And then this one's also a hexanoic acid. So 1, 2, 3, 4, 5, 6. Just for fun, let's put carbon number 1 over here this time. 2,3-diethyl. So 1, 2, and then 3. So 2,3-diethyl hexanoic acid. 3,3,5-trimethyl 2-chloro-hexanoic acid. Feel good on these? We're good on those.
Why is there a line between fluoro and hexanoic?
There shouldn't be a dash right there. You're right. There shouldn't be a dash right there. It should be continuous. 2-chloro-hexanoic acid. Yeah, that's just a typo. There should not be a dash there. Good catch. Okay, so when we have 2 carboxyl groups, we call that a dioic acid. Just like when we had 2 aldehydes, we called that a dial, right? If we have 2 carboxyls, that would be a dioic acid. And it's not butadioic acid, it's just butane dioic acid. Okay, so you don't change the parent at all. You just call it butane dioic acid. Okay, so this is a 4-carbon chain, 1, 2, 3, 4, or 1, 2, 3, 4. It really doesn't matter here, right? Because there's no substituents. So this would just be called butane dioic acid. And then if there were substituents, right? Let's pretend there was a chlorine right here. That would be 2-chloro-butane dioic acid. Okay, make sense? And if we're talking about aromatic, right? So if the parent molecule is a benzene ring, then we would call that benzoic acid, right? And then we would have any other substituents on there, just like we've already talked about. So for instance, if you had this, right? You could name this what? You could name it 2-bromo, and then the parent molecule is benzoic acid, right? Or what's the relationship when they're next door to each other?
Oh, it's an L.
Oh, right. Or you could say O-bromo, benzoic acid. See what I'm talking about there, right? This is the parent molecule. And then any substituents, or maybe, you know, it was over here, that would be M, or over here, it would be P, right? So when it's on a benzene ring, that's the only aromatic that you're gonna have to worry about in this class. Because the only aromatic molecule we dealt with at any level is a substituted benzene, right? There are lots of aromatic molecules that exist, but the only one we look at in elementary organic is benzene, substituted benzenes. Right, so there would be benzoic acid. You could name this 4-amino-benzoic acid or p-amino-benzoic acid, right? What if you had 2 substituents? Well, you couldn't use the meta-ortho-para, right? Because that only works if there's 1 substituent. But you could just call it 3,4-dichloro-benzoic acid. So you might see some of those on the homework sets. Okay, so now let's talk about esters. Since we made esters, let's talk about them now. So, like I said, in an ester, that H is gone, right? Because a carboxylic acid is COOH, so an ester is just COO, right? And it's on the interior of a molecule. So a carboxylic acid has to be on the end, right? Because hydrogen can only form 1 bond. It's not like you can have the chain continuing on the other side of a hydrogen, right? Hydrogen stops the chain. Whereas an ester, because there's no hydrogen, it's on the interior. So it can have anything on that side, anything on this side. So could this even be a ring? Could these two be looped around to each other, make a ring? Yeah, yeah. Just like you can have a ketone in a ring, right? You can't have an aldehyde in a ring unless it's sticking off the ring somehow. You can't have a carboxylic acid in a ring, right, unless it's sticking off. But you can have an ester inside a ring, because who cares if these two are bonded to each other, right? That's not going to affect the ester. Esters generally smell pretty good. It's a picture from your textbook. So a lot of these esters you actually see as things that we like oils, you know, used as fragrances and that sort of thing. Banana oil, pineapple, raspberry, oranges, etc. Right? They're not highly stinky like thiols. The SH functional group is something you run from. It really stinks. But the esters, those generally smell pretty good. Also, aspirin contains an ester, right? There's the ester in aspirin. And then there's another ester. You may have seen, you know, in like your products that are tingly and help with your muscles. Okay, now because they are on the interior, their boiling point isn't going to be as high as a carboxylic acid. But would an ester's boiling point be higher than the ketones? Yes, that extra oxygen will make it more polar, right? But it's not going to be a humongous difference. It's going to be higher, but it's not going to be like 50 degrees higher, right? You will notice a difference, but it's not going to be humongous. Like an aldehyde versus an alcohol kind of thing. So here is a figure from your textbook. I wish it would have put an aldehyde in there just as comparison, but it didn't. Oh well. Right, there's butane. I always pick on poor butane. There's the ether analog. There's the ester analog. Right? There's the alcohol analog, and then there's the carboxyl analog. Right? And so when we name esters, this is why we talked about esterification, because the way we name esters is based on how the ester was made. So if you're looking at an ester, you kind of have to break it down. You need to name the part that came from the alcohol first. In other words, what side is attached to the O? Remember when we just drew esters a few minutes ago? It was carboxyl, O, blah, 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 right? The O, blah, blah, blah. That comes first. And then the part that came from the carboxylic acid, in other words, the part that's attached to the carbonyl, goes second with a suffix OATE. Now I could flip it around 180 degrees, right? If I take that molecule and rotate it, you would still need to identify the part that came from the alcohol and name it first, and the part that came from the carboxyl and name it second. Okay, so don't let that throw you off. All the ones we've done so far have had carbonyl, then O, right? But what if I had O, then carbonyl? You would have this part first, as opposed to this part first. So if I take a molecule and rotate it, just to see if you're paying attention, right? Watch out for that kind of little trick. So here's an example, right? This is the carbonyl carbon, and this is an ethyl. Now watch out. A lot of students make this mistake, so please don't do it. Don't forget to count the carbonyl carbon as part of this chain, right? It's ethyl. A lot of students would say that that's methyl, but it's not, right? That carbonyl carbon does count as one of the carbons in the chain. So this is ethyl, and then this part right here is methyl, right? That's not a carbon, that's an oxygen. So this would be methyl ethanoate. Does that make sense? This part came from the alcohol. This part came from the carboxylic acid. So methyl ethanoate. If I gave you this molecule and said, okay, how would you synthesize it? You could break it down, right? This part came from methanol. This part came from the carboxylic acid. And again, this is an example where it's been flipped, right? All the ones we've seen so far have had the carboxyl first and the O second, right? But we took it and we flipped it. O first, carboxyl second. This part came from methanol. This part came from ethanoic acid. Make sense? Okay, so name this, and then just for good practice, identify which alcohol and which carboxylic acid it came from. I'll pause it and give you a chance to try that. All right, let's look at this one, see what we got. when we break this down, what part did this come from? The carboxylic acid or the alcohol? All right, this came from the carboxylic acid. What carboxylic acid specifically did it come from?
Ethanoic.
Right, this came from ethanoic acid. And what part did this come from? That's the alcohol piece, right? It came from what alcohol? 1, 2, 3. Propanol? Do we just leave it like that? 1 propanol, right. So what's the name? Do you put the alcohol component first or the carboxylic acid component first? Okay, so what would the name be when we take this? Okay, so we break it down. Oops, I moved it on the screen. Propyl, ethyl, propyl, because that's from the propanol, and then ethanoate. I moved this picture so I could write on the board easier. So this is from 1 propanol, right? So it'd be propyl. And then this is the new parent chain, so to say. And then the subscript, and that's subscript, the suffix is OAT. Okay, so propyl ethanoate. Does that make sense? I forgot that I moved the slide before I wrote on the screen, so it messed up my PowerPoint. Lost points for flow there. Does it make sense? I think I've got a couple more for you to try. Yes. So name these. And just for practice, let's identify the alcohols they came from as well. I'll pause the recording. All right, let's go over these. So, where do we want to begin? Do you want to start with the alcohol component or the carboxylic component? Okay, that goes first in the name. So what alcohol, what side is the alcohol side? This side, right? So this came from what? Right, came from methanol. You don't need a 1 on methanol, right? Because that's just CH3OH. There's no other place you could put an OH other than carbon 1. And this came from what? 1, 2, 3, 4, right. Butanoic acid. So when you put the two together, what do you get in terms of the name?
Methyl.
Yes, methyl. Butanoate, yes. All right, let's do the next one. Now notice what's the difference between the A and B?
This side the alcohol's on.
Right, I've just flipped it. Okay, so don't let that throw you off. The carbonyl does not have to come first in terms of reading it from left to right, right? This molecule is perfectly legit. It's just flipped from what we've looked at so far. So where's the part that came from the alcohol? It's now on the left, right? So what alcohol did that come from?
Ethanol.
Right, that came from ethanol. And again, you don't need the 1 on ethanol, because if the OH is here, or if the OH is here, it's still number 1. And then what did this come from? Right, 1, 2, 3. This came from propanoic acid. So the name ends up being what?
Propyl, no, ethyl.
Ethyl, right.
Propanoic.
Propanoate, good. Good. Do you feel good about how we do this? All right. Oh, I was just showing where I broke it down. Do you want to go through some more, or are you feeling pretty good? Think you got it? Okay. So, right, this one would be butyl pentanoate, 1, 2, 3, 4. That's the butyl pentanoate, 1, 2, 3, 4, 5. Right, that's where the pentanoate comes from. And this would be hexanoate, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I'll give you a second to draw these just for good practice. Ethyl pentanoate and propyl butanoate. Okay, let's draw some esters. So if it's ethyl pentanoate, let's start by drawing the carboxyl group. I mean, not the carboxyl group, the ester group, and then just figuring out what goes on each side. So what's going to be attached to the O? The ethyl, right. So that's going to be how many carbons? 1, 2, good. And then what's going to be attached here? Now be careful, do I add 5 additional carbons? Would I go 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. No, why not? Because that's a 6-carbon chain, right? This counts as one of the carbons. So technically I'm only adding 4 additional, right? Because this counts as one of them. So 1, 2, 3, 4, right? 1, 2, 3, 4. Oh, there we go, 5. Pent, this counts as one of those. We're going the other direction for this one. Propyl, again, we can start by drawing our functional group. Let's just draw it going this way for fun. So we get used to seeing things from both directions. What's going to be attached to the O? 3 carbons, right? So 1, 2, 3, right? 1, 2, 3. That gives me the propyl. And what's going to be attached to the carbonyl? 3 additional, right? Because that counts as one of them. So 1, 2, 3, 4, right? 1, 2, 3, 4. That gives me the butanoate.